Hi class, this lecture is on acceleration. And although Galileo is more known as an astronomer, he's actually the person who developed our modern ideas about motion and in particular about acceleration. So prior to him, the basic ideas about motion were summarized by Aristotle. And some of his findings were that objects fall naturally downward, so that was regarded as the most natural motion. Objects require a force to move horizontally. So if you push a book across a desk, if you stop pushing, then it stops moving. Okay. And finally, Aristotle believed that heavy objects fall faster than light objects. Example here is rocks and feathers. You could also take a book versus a sheet of paper, and you see the heavier object falls faster. Okay, but Galileo really initiated an experimental study of motion, and he came up with the idea that without air resistance, any two objects, when dropped, would fall with equal rates, independent of mass, size, and shape. And this idea was actually tested on the moon. So let me show you that real quick here.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? This proves that Mr. Galileo was correct in his findings.
Okay, you don't actually have to go to the moon to do that experiment. You can actually do this one at home. I mentioned earlier the book and the sheet of paper. Just try putting the sheet of paper on top of the book and then let them fall, and you'll see that the paper, since the book is blocking all the air resistance, the paper will fall at the same rate as the book. Okay, another thing Galileo noticed was if you have a ball rolling on a ramp, if the ramp is going up, the ball's rolling up, then the ball will slow down. And if the ramp is sloped downward, the ball will speed up as it rolls down. Okay, so Galileo concluded that if there were no friction, then a horizontal ramp would allow the ball to roll forever. Okay, so he regarded the natural motion as being one that doesn't change. And Galileo and also Descartes were responsible for developing what's now called the law of inertia. The idea is that a body that's subject to no external influence or force will not change its velocity. So if it's at rest, it will stay at rest. And if moving, it will keep moving in a straight line at an unchanging speed. Okay, so we've talked about velocity before, and velocity is what you measure on a speedometer. Actually speed, which is the magnitude of velocity. So that tells you how fast you're moving relative to normally the Earth's surface. But if your velocity is changing, then you're accelerating. Okay, so acceleration is the rate that the velocity changes. So if you're looking at your speedometer, acceleration would be how fast the needle is moving. Okay, how fast you're changing speed. Okay, so the mathematical formula for that, remember that velocity is the change in position. Remember this Greek letter delta stands for change. So delta x divided by delta t is the change of position divided by the change of time. that's equal to velocity. And you can multiply both sides by the change of time. You get change of position as velocity multiplied by change of time. Okay, so acceleration has a similar formula, but the thing that's changing now is the velocity rather than position. So acceleration is the change in velocity divided by the change of time. So it's the rate the velocity is changing. And we could also calculate the change in velocity as being the acceleration multiplied by the time interval or change of time. So velocity would be the slope of a graph of position versus time, and acceleration would be the slope of a graph of velocity versus time. Okay, so let's look at some sample graphs. Let's start with this one, acceleration versus time. And suppose we have constant acceleration. Okay, that's all we're going to worry about in this class. So if the acceleration is 0, you have a horizontal line with at the 0 value. If acceleration is positive, you have a horizontal line with a positive value. And if it's negative, you have a horizontal line with a negative value. Okay, very simple. The slope is always 0 if you have constant acceleration. Okay, now if we look at the velocity graph, remember we said the velocity changes when you're accelerating, and the acceleration is equal to the rate the velocity changes. So the change in velocity over the change of time, which is the slope of the velocity versus time graph. So you can see here the vertical change is the change in velocity, and the horizontal change is the change of time. So that ratio, delta v over delta t, is the slope of this line. All right. So if you have a positive acceleration, you have an upward slope on your velocity line. So velocity is steadily increasing with time. If you have a negative acceleration, then the velocity is steadily decreasing with time. And of course, if you have 0 acceleration, then you just have a constant velocity. Okay, but that velocity doesn't have to be 0. It could be actually a constant at any value. Okay, just looking at the equations, if we solve for velocity, we would say there's some initial velocity plus the acceleration times the time interval. You could put delta t there, but I left that out. So the v minus v0 would be your delta v. Okay, so the velocity is the initial velocity plus acceleration times the time. Now, if you want to know what the average velocity is, you would take this value for your final velocity and you would average that with the initial value, which is v0. Okay, and so when you do that, the average velocity is your initial velocity plus half the acceleration times time. So you're averaging this quantity with just v0, so the acceleration times time only comes in with the weight of half. So average velocity only changes half as fast as the final velocity. Okay, now let's look at a position graph. So remember the position graph, the slope is the change of position over the change of time is the velocity. So if you have a constant acceleration, that means the slope of your position graph is changing. So it's going to be curved. All right, and at any point you can pick some change of position and change of time and calculate the velocity roughly at that point. You have to actually pick a couple points that are slightly separated. But you can calculate a velocity at any point and you'll see it's changing. Okay, so for velocity that's increasing with positive acceleration and positive velocity, so I'm actually starting here more or less 0 velocity coming out horizontal, and the velocity is getting more and more positive, so you have this upward curve. If you have a negative acceleration with a negative velocity or decreasing velocity, starting from 0, you'll see that it's curving downward. Okay, now you could imagine two more cases here. You could have a negative velocity and a positive acceleration, in which case you would be coming down, let's say from the left, like kind of a mirror image of this curve, like that. And you could have a positive velocity and negative acceleration, in which case you'd be coming up on one side, but getting slower and slower. Okay, so those are your position versus time graphs. And if you look at the formula, remember change of position. So x minus its initial position. Change of position is the average velocity times the time. So if we take that expression we had for the average velocity, this v0 plus half acceleration times time divided by 2. If we now multiply that by the time, we'll get v0 times the time, and we'll get 1/2 acceleration times the time squared. So that's what this formula over here is for the average velocity times the time. Okay, so a little practice for you. Think about what would be the signs of velocity and acceleration for this graph. I'll just give you a few seconds to think about that. Okay, hopefully you come up with these three properties. So on this part of the graph, the velocity is positive, okay? But since the slope is decreasing, that means you have a negative acceleration. On this part of the graph, the velocity is negative, okay, because the position is decreasing, right? Whoops. Position is decreasing, and the acceleration is still negative, even though the slope is getting steeper and steeper, so it's going faster and faster, but it's going faster in the negative direction. So we still call that a negative acceleration. Okay, so that's something to keep in mind. Okay, so if we have an object in what's called free fall, which means it's only influenced by gravity, near the Earth's surface, the gravitational acceleration is pretty nearly constant. It's downward, which is why you'll sometimes see a minus sign. Generally, g is positive, but the acceleration is downward, 9.8 meters per second. And we can round that off usually and just say that's minus 10 meters per second squared. Notice the unit here, it's 1/seconds here, and then another 1/seconds here. So you end up with 1/seconds squared. Okay, in other units, it's 32 feet per second squared, or 22 miles per hour per second. Okay, so with constant acceleration, that means your velocity versus time would be a straight line on a graph, and your position versus time would be a parabola. Okay. Now, if you look at the height versus distance, so imagine you toss something in the air and then you just sort of track its path through space. Since the horizontal position is just the horizontal velocity times the time, and the horizontal velocity is constant because gravity only acts vertically, it doesn't act horizontally. So really, you can more or less substitute the horizontal position for the time. So it's going to have the same shape graph. So height versus distance will have the same shape of graph as the height versus time. Okay, and one thing to keep in mind is acceleration causes a difference from the constant velocity motion. Okay, so for example, if I have two balls and let one of them drop and shoot the other one out horizontally, and then film them with strobe light so you only see the positions at certain times. You can see here the two balls always maintain the same height, so they have the same vertical velocity, vertical acceleration, and vertical position, even though the yellow ball also has a horizontal velocity. Okay, So one thing to be careful about with acceleration is keep track of what we mean by the positive direction. So in ordinary usage, we would say if an object is speeding up, then it's accelerating, and if it's slowing down, it's decelerating. But in physics, we don't use that same terminology. So we would have some direction defined as being positive, let's say here to the right. So if the acceleration is to the right, so it's increasing the velocity towards the right, then we say that's positive. So, and then if the acceleration is increasing velocity to the left, we would say that's a negative acceleration. Okay, so if the acceleration and velocity are in the same direction, then it's increasing speed. But you can also have velocity to the right and acceleration to the left, and we would say that's a negative acceleration. Or you could have velocity to the left and acceleration to the right. So we would call that a positive acceleration, even though it's slowing down. Okay, so in physics, whether the acceleration is positive or negative just depends on which way it's pointing. In what direction is the velocity changing? Okay. All right, so it's quite different from the ordinary usage of these terms, acceleration and deceleration. So deceleration refers to the direction of the acceleration relative to the velocity, not its absolute direction. Okay, so if you toss a ball up in the air, you're going to give it a positive velocity, assuming positive is upward. But gravity is going to be initially slowing it down. Gravity is always pulling downward. So the ball's velocity is changing in the downward direction, so that's a negative acceleration. And then at some point it reaches its peak. And then as it starts to come back down, the velocity is still getting more and more negative. So it's still a negative acceleration, even though it's going faster and faster. Okay. You can also have acceleration perpendicular to the velocity, in which case you're changing the direction. So for example, you could have an object going at a constant speed in a circle, like an orbit. And even though the speed is constant, if the direction is changing, that's also called an acceleration. So any change of velocity is considered an acceleration. And that brings us to orbits. As an object moves past the Earth, it's being accelerated towards the Earth. Okay, so if it starts out slowly, like just tossing something in the air, it will fall back, nearly straight down. Okay. On the other hand, if you have a meteor or something that's going very fast, it'll be accelerated towards the Earth, but only for a short time, and so it may just slightly deflect the path of the object. Okay, but if you get an object going more or less the right speed, then you can actually get into orbit. So you can have an object that's constantly falling towards the Earth, but as it falls towards the Earth, it's also moving past the Earth. So, if you consider the Earth as being, along this line here, yes, it falls down to where the Earth, the same level as the Earth, but it's moved past the Earth. Okay, so now it's over here. And then now it's falling towards the Earth again. But again, as it falls, because it's got this other motion, this circular motion, it's falling towards the Earth but never hits the Earth. So it just goes around in orbit. And I have an example of that. Let's see. Here, it's a little example called Newton's Mountain. And the idea is you have a cannon up on top of the mountain that's shooting a cannonball. So if we fire the cannonball, we see it falls down on the Earth. If we make it go a little faster, let's go like this fast here, reset it, then you see it goes farther. And of course, if you go fast enough, then it keeps falling towards the Earth, but it keeps missing the Earth. Okay, so don't try that at home. All right, but that's something that Newton thought of. Let's go back to our slideshow here. Now, there's an interesting thing about satellites, is you can have a satellite that goes around the Earth once per day. And if it's over the equator, remember the Earth is also spinning once per day. So the satellite can actually be over the same place on Earth as it goes around once a day. And if it's doing that, you might as well just hang a rope down, and then you could pull things up the rope to the satellite. Okay, NASA actually looked into this. It was an idea called space elevators. And what they concluded is, yes, it's physically possible, but would be exorbitantly expensive. But it is kind of amazing that you could hang a rope down, pull stuff up into space, even though there's nothing holding the satellite up. It's just orbiting. Okay, I just want to caution you here about this idea of proportionality. So if we have a constant acceleration, we would say the velocity is proportional to time. So with constant acceleration, if you double the time, you would double the velocity. Okay, so velocity is proportional to time. But remember, if we had a constant distance to travel, where velocity is distance divided by time, so in that case, the velocity is inversely proportional to time. Okay, so whether it's proportional or inversely proportional depends on what's being held constant. Okay, if you have constant acceleration, then the velocity is increasing with time. But if you're traveling a constant distance, then the longer it takes, that means the slower that you're traveling. Okay, so this idea of proportionality, just keep in mind that always depends on what is being held fixed. Okay, and for accelerated motion, the distance is actually 1/2 acceleration times the time squared. Okay. And remember that a graph of velocity versus time, the slope equals the acceleration. Okay, so here's another little practice for you. Suppose you have a constant positive acceleration. Sketch a graph of velocity versus time. Tell me what would be the equation for velocity, and then sketch a graph of position versus time. Okay, I'll give you a moment to try that. Okay, this is what you should have come up with. So for a constant positive acceleration, the velocity should be increasing linearly with time. And the equation for that is that the velocity, or more accurately would be the change in velocity, is the acceleration times the time. Okay, and the position versus time should have a curvature, so it should be curving upwards. Okay, so that's your simple example.